Yeah, without further ado, I'll cover what's new in 0.9.0. This is a pretty big release, a good number of possibly breaking changes, but there's a lot of things that we needed to deal with here. Obviously, the first thing I want to call out is that over 600 commits from 140 different contributors, and 82 of those are new contributors. This was a release that happened over about 4 weeks, I think. We meant to do 2 weeks, and then we had another 2 weeks of testing and bug fixes. So that's 20 new people per week that are contributing to vLLM, which is pretty crazy. We're really proud of that number. So obviously a really big thing is we upgraded from PyTorch to 2.7.0. Um, and with that, we now build for CUDA 12.8 by default. This was pretty important. This is necessary to support Blackwell. This does complicate things a little bit because the PyTorch default wheel on PyPy is built for CUDA 12.6. So particularly if you're on a Blackwell machine that requires CUDA 12.8, you need to have a special flag to install the right version of CUDA with PyTorch. But we've updated the docs to make that pretty easy, and especially if you use UV, which we recommend instead of the vanilla pip, you can actually just pass in this Torch backend auto flag, and it will pull the right version of Torch depending on your CUDA driver installed, which is really nice UX. Um, so there's that. Of course, we talked about NVIDIA Blackwell support. We've been working on optimized kernels for this. One of the things that isn't supported on Blackwell is Flash Tension 3. So we highly recommend making sure Flash Infer is installed and enabled if you want good performance on B200s. Um, so try that out. Let us know if you run into any issues. It will still run on Flash Tension 2 if it can't find anything else by default, but performance may vary. As I mentioned before, there's been a lot of progress in EP, expert parallelism, DP, data parallelism, and PD, disaggregated prefill and decode, as we're scaling vLLM to larger scale inference. Um, a lot of this goes into support for disaggregated serving frameworks like LLMD and LM cache. Um, so, so yeah, check out those things if you're interested in it. Ask questions, certainly. And then one thing you'll notice on the docs.vlm.ai, we've moved from Sphinx to make docs, so it has kind of a refreshed look, a lot better search. But we're still, working out some kinks in the docs. So definitely report any funky docs that you find, and we're improving this day by day. Now, in terms of model support, there's a good handful of new models supported. There's including more and more Mamba hybrid models, which is really cool to see for us interested in local attention. Um, yeah, some embedding models, nomic embedding models, it particularly has been a pretty highly requested model. So we're happy to get that in. And then there's been a lot of progress on the hybrid memory allocator. This is like a sort of a refactor towards how KV cache is managed in vLLM to more efficiently allow for management of models where, not every layer has the same type of attention. So, this is important for Llama 4, where three out of every four layers has a sort of local attention, whereas one out of every four layers has a global attention, or models that use sliding window, or models that use state space models mixed with global attention. Currently vLLM has some hacks to represent this non-uniform KV cache memory, and so we're glad to make progress on the hybrid memory allocator. There's been a good number of performance improvements on DeepSeek models, as well as support for Qwen models with really long context length, like the Qwen 2.51 million. And then we've been working on several optimizations for multimodal models in general, but particularly, Qwen VL had some particular enhancements with MROPE. Um, yeah. Another pretty important thing, if you're interested in low latency, low batch size throughput, is supporting full CUDA graphs in V1. If you followed V1 development, we've had piecewise CUDA graphs since the beginning, but there's still some use cases for full CUDA graphs, particularly when the model execution itself is pretty small, where the CPU overheads are still there. So this is an experimental feature you can opt into through the compilation config. So definitely check that out. We have some initial work on enabling sequence parallelism, which is pretty cool. It's not exactly performant yet, but we think this will be pretty important for long context length scaling in the future. And a few other optimization and performance features. There's a lot of new user features. There's a lot of work on this release in properly defining our deprecation strategy and starting to more properly and transparently say what arguments we're going to deprecate and committing to a two release timeline before removing features like breaking changes. So we've definitely heard the people that want to have more transparency in how things are being deprecated. Various front-end improvements, various quantization improvements. One of the things that were added are there's now initial support for NVFP4 models and MXFP4 models, which are obviously the new FP4 formats supported on the latest NVIDIA Blackwell GPUs and AMD MI350 GPUs. Some simplifications to reasoning parsers, a lot of work on speculative decoding. Support for Eagle 3 has been the real big highlight there, and now there's a good bit of optimization work to do on that, which we've already added CUDA graphs and torch.compile to it. So look for more performance and progress being made on speculative decoding. Um, yeah. Another thing, if you're using the transformers backend, we're expanding the variety of models that can be supported there. So now we can have sliding window attention, interleaved support for models. We're still working on multimodal model support and embedding model support. So stay tuned for that in the next couple of releases. And then on the hardware side, there's a whole bunch of new kernels and support put in there. I won't read all of these, but you can see the variety of hardware support in vLLM is pretty great. Just to cover like some notable changes, CUDA 12.4 is not supported anymore because PyTorch doesn't support it. So now the only available versions that we have in all the various places is CUDA 12.8, CUDA 12.6, and then we still build for CUDA 11.8 for the people still on those old ones. Top K now matches behavior with transformers a little more closely. And also the seed has been changed. Before we kind of had a random uninitialized seed, but we got some feedback that we should have a sort of fixed seed that runs. So if you depend on that behavior, make sure to make note of the change here, and you can still override this by setting seed to none, I believe. There's been a lot of security improvements. If you're interested in the security of vLLM and how we deal with security advisories, definitely check out the announcements channel on the vLLM Slack. Russell has been doing a lot of work in triaging and dealing with the security advisories, and we've been addressing most of them. And I think most of the other things are kind of just tidbits or little developer features. So that's all on the latest vLLM release. Feel free to ask questions in the chat. But for now, I'll pass it off to Luca and Richard.
All right. Hi, everyone. I'm Richard. I'm a software engineer working on the PyTorch team at Meta. Luca's on the call. I'm going to start first. So today we're going to be talking about introduction to torch.compile and how it works with vLLM. So I'm going to give a quick intro to torch compile first, and then I'll discuss like how vLLM uses it. Torch compile is a just-in-time compiler for PyTorch code. So you can write a function. It uses torch ops. This one calls sine, cosine, and then adds the two numbers together. And you can slap the torch compile decorator on it, and it will just make your function go faster. There's a couple different ways to use it. You can decorate a function like this. You can also decorate an in module as so. You can compile the module and then just run it. So why use torch compile? Our value proposition is that torch compile offers you pretty good baseline performance to save you time from writing custom kernels. Given any specific model or a specific function, you could probably sit down for like hours, days, or weeks just writing a really fast kernel for it. But if you don't want to do that, and if you want something that gives you like really like 80 to 90% of the way there, like just use torch compile. Put torch compile in your code. It'll make your code run faster, like so that you don't have to invest a lot of time into actually making your code run faster. And some examples like are like on the left side, this was a Twitter post from some of the Hugging Face folks when they enabled torch compile on Gemma 3 and transformers. They saw like 60% speed up, which is great. On the right side, PyTorch compiler team, have a performance dashboard of just miscellaneous models. We track like how things like run, like how things run, like if any things are slower or faster with torch compile. Numbers here are like currently between 1 to 2, but we've seen like numbers speedups as high as like 8x sometimes with torch compile. The main idea of using torch compile is that like it offers you like really fast performance on just a variety of different models. Okay, I'm gonna talk really quickly about how Torch Compile works. Torch Compile has a front end, has a back end. The front end just does initial graph capture, given some Python code, like the model on the left. Model on the left is doing like linear ReLU, linear ReLU. Um, and the function we're compiling also appends a tensor to a list, a global list. Torch Compile like looks at your code. It has a custom bytecode interpreter that will run your code and extract a straight line graph out of it. So it will extract a graph of only PyTorch tensor operations. It'll also, in addition to the graph, it returns you some bytecode, which is some glue code that does any Python side effects that might exist in your function. So like this function has like tensor operations. It also has a side effect of appending to a list. So torsion file gives you this graph, gives you some bytecode, and that's what our front end graph capture does. The front-end graph capture does not have to give you a single graph. It can give you multiple graphs. This is a feature. Sometimes you'll write some Python code where like it just has things that are just not supportable. For example, like you've got this function, you're doing some tensor operations, you're calling torch.save, and then you're doing some other tensor operations. The torch compile does not really support like disk IO operations. So what it'll do is it'll capture one graph for your first tensor operations. It'll run like the torch save, then it'll capture a second graph for your non-disk IO operations, these tensor ops, and then it'll just return from there. So effectively, it's capturing two graphs here, and it's running the save in the middle. All right, so we'll talk about the backend. Once you have captured a graph via the torch compile front end, the backend takes this graph and then it spits out some really fast code. It'll take the graph, it'll try to run optimizations to it. It will try to like turn it into Trident code, and then it'll run that. For this particular sequence of operations, like it just calls sine, cosine plus one, we'll take all of that, we'll lower it into a single Trident kernel on the right. One of the optimizations Torch compile does is just fusing these pointwise operations together. It can also fuse reduction like operations together as well. Another thing Torch compile does is auto-tuning. When you're writing a Trident kernel, sometimes you'll try to auto-tune it to figure out like what the best like configurations are. Torch compile does that automatically, depending on the configurations you pass it. So we will auto-tune, for example, the block sizes for said output code, output Trident kernel. Some other optimizations. Most of the flops in the model usually just goes through matmul operations, and so we'll try to select the best matmul for you. Um, Spoiler alert, torch.mm is not always the fastest matmul. So given like a torch.mm call or torch matmul call plus some pointwise operations, we'll try to benchmark torch.mm versus a trident matmul versus a cutlass matmul that's hidden behind a config and perhaps even other matmuls in the future, and then choose the fastest matmul to use in your case and then just run that. Another optimization is CUDA graphs. CUDA graphs are built into torch.compile. If you pass max autotune to torch.compile, it will use CUDA graphs. CUDA graphs is this technology that lets us on an NVIDIA GPU record a sequence of kernel launches and then replay the kernel launches in the future. This saves the overhead of just launching the CUDA kernels, and it reduces the overhead there. So it's kind of difficult to use a raw CUDA graphs API safely because CUDA graphs, like it records CUDA kernel launches, replays those. If there's any compute on your CPU, like any CPU kernels that are running, those do not get recorded, those do not get replayed. And so if you have like any CPU compute, like you can, it, and you're using the raw CUDA API, it may result in silent incorrectness. Torch Compile fixes that for you by just analyzing your code, figuring out if you have any like unsafe operations, and just like graph breaking when you do. All right, so I'm going to talk about how vLLM uses Torch Compile. By default, vLLM uses torch compile. Torch compile is on by default in vLLM. You just like when you're vLLM serving a model like online, or if you're running it offline, torch compile is just on. You can pass -- enforce eager like in either of these to turn torch compile off. So this is a simple mental model for compilation. We'll talk about the simple mental model, and then I'll tell you how vLLM actually customizes this for its requirements. So it's a very simple model for compilation. You have some model, you have some example inputs. We're going to, the compiler captures a graph. It runs some backend optimizations to a set graph, and that produces a compiled artifact. The first optimization vLLM specifically does is caching. So vLLM has requirements in that we want there to be no recompilations during model serving. Torch.compile is a just-in-time compiler. It can recompile. vLLM like has some code to make it so it does not recompile. The way this goes is like on a cold start, like when you're booting up a model on a like machine for the first time, vLLM will run the compile step, and it'll save your model like produced artifacts to a torch compile cache. On subsequent like on model serving time, like on this machine, on the first machine, it will just load up the artifact and it will run it. If you're spinning up multiple machines, new machines, and during cold start, if you copy paste the cache directory over, if the cache directory exists, then vLLM will try to read from the cache directory and reuse those cache artifacts. So this is really useful for like auto scaling use cases where you just got a server up. You got a server up, it goes down, it goes up, comes back down, and you might be using different machines. Like just make sure to copy paste the cache directory across the machines. Dynamic shapes. So by default, vLLM like uses captures a single graph with dynamic batch size, and then asks torch.compile to compile a graph for said dynamic batch size. And then the graph just kind of artifact works no matter what the batch size is. And you can squeeze more performance. We've seen like 5 to 10% more performance by specializing on specific batch sizes, especially for batch size one. The way you do this is you pass compile sizes to vLLM. Also, like compile sizes in the compilation config, in the online case, or same thing in the offline case. And this will tell Torch Compile to specialize on batch size 1, 2, and 4 for your model serving session. When Torch Compile specializes on these batch sizes, it will do a separate compilation for each batch size. So this will increase your compilation time, but the performance gains can be worth it if you know that you are going to be using these batch sizes, specific batch sizes a lot during inference. code graphs. So vLLM also uses code graphs. It actually uses this thing called piecewise code graphs, in that in your models, some of the operations are not cryptographable. In particular, the attention operation is not always cryptographable. And so vLLM will use torch.compile's frontend to do a graph capture. It will split the graph. Um, it will split the graph between operations that are not actually cryptographable. In this case, on this slide, the attention operation. It'll compile each of the graphs that are cryptographable, and it'll run like those graphs, those compiled artifacts under cryptographs, and then it'll run the things that are the attention op, and then it'll run the graph that is cryptographable under cryptographs. Okay, so I think one last thing I want to talk about is flex attention. We're integrating flex attention into vLLM. This is coming soon. Flex attention is this API that lets you implement a bunch of attention variants really easily in a few lines of PyTorch code. In particular, like to use attention today, like you would probably use like a flash attention kernel, or like just some like low level attention kernel. And if you want to like customize this attention kernel by adding things like an alibi bias, you sort of need to copy paste the whole kernel, like tweak it to like have your like special attention logic, and then compile it, or just use Trident to actually run it. And flex attention is this API that makes it so that that entire process is just handled by the compiler. As an example, if you wanted to do your standard bidirectional attention, you can just call flex attention, and you pass it this no-op score mod. If you want to do some relative position encodings, you can just add it to your score mod function, pass it in, and behind the scenes, torch.compile uses like the function you passed into flex attention. It'll convert it into like some Trident code, and it'll straight up just lower it into a Trident template for flash attention to actually make it run fast. All right, that's all for me. Luca's going to be up next.
All right, can you all see my screen all right?
Yep.
Perfect. Thanks. So yeah, thanks Richard for the great overview of Torch Compile and how we use in vLLM. And I'm going to speak very briefly about how we use custom Torch Compile passes. And I'm going to dive really deep, so I just want to give a quick overview first. I'm going to talk about why we use custom Torch Compile passes. Then I'll talk a little bit about how we implemented them and how they work. And then we all care about performance here, right? So talk about the performance we gain from it. And then finally, talk a little bit more about the general status of torch compile passes, of custom torch compile passes in vLLM. So why do we want custom passes? We know about this performance simplicity trade-off in vLLM, right? So we have these model definitions that are very declarative and expressive. So when model writers write a new model definition, they care about what's in the model, like what it does, not how to achieve that, right? So we want them to be simple and just express what the model is doing step by step. On the other hand, vLLM users want maximum performance, right, at all costs. So these things can be at odds sometimes. Sometimes the best performance can only be achieved by breaking abstractions and making model definitions more complex, and we don't want to do that. So instead, we can achieve both of these things, both simple model definitions and maximum performance, using Torch Compile. And that's done with the graph capture, right? So Richard explained this. We kind of capture the model execution end to end into a linear graph. So all the abstractions are gone. So we can use any abstractions that we want to make things simple. And then the end still get kind of a linear graph where things going across abstractions can still be optimized and get better performance. So why do we need custom passes in Torch Compile? Sometimes we have custom kernels and we want to do graph transformations on them. And then sometimes we want to do additional optimizations that are not yet or not present in Torch Inductor. So let's look at a quick Llama model capture example and then see how a custom pass can improve performance. So on the left, we have a condensed version of the Llama model definition. So this is pretty much what you can find in llama.py in the vLLM / I think model executor. I've omitted a few things so you can see the kind of some of these things that are constructed on the left are missing a bunch of lines for config. I've omitted some control flow. I've omitted a little bit of pipeline parallelism support. But in general, right, like a Llama model consists of a bunch of Llama decoder layers, and a Llama decoder layers consist of an attention, an MLP, and an RMS norm. And then the MLP and attention are seen above. Um, right? So we have this and it looks really nice. It has all the abstractions so that we don't have to repeat ourselves. So everything makes sense. And then when we trace this with Dynamo, with the front end of Torch Compile, we get this graph that we see on the right, right? So all the control flow on the left, all of the kind of classes, function calls, all of that goes away. And all the CPU overhead goes away. So we have kind of like a linear efficient graph on the right. And then all these operations can also get fused. So in the end, we get efficient code. But what if there are custom kernels involved, right? So let's say for RMS norm and for CLU and for quantization, we might have some custom kernels. And those torch compiled cannot just automatically fuse because it doesn't understand them natively. So instead, we use custom passes for that. And let's look at the example I mentioned. So fusing the CELU and mol operation, the activation function, with a quantize operation following it, right? So on the left, inside the MLP definition, we can see inside the forward function that after the activation function, we execute a down projection. And if this down projection is quantized, it consists of one quantize and then a linear layer, right? And the quantize is a pretty element-wise operation, so it's very memory bound. A CELU and mol activation function is pretty memory bound. So ideally, you want to fuse them, them at the same time, and reduce the cost and increase the performance, right? We could do this by changing the model definition, but by that we would have to modify the abstractions that we use and change the model definition, and we don't want to do that, right? So on the right, we see the trace graph, and we can see that these operations are just, a list of torch and some custom operations. And so the way we fuse them is in a custom pass, we use something called a pattern matcher. So pattern matcher in Inductor is this really nice utility that basically lets you register a pattern and a replacement. So in this case, we register a pattern where a CELU and mol call to the custom kernel is followed by a call to the static scaled FBA quant kernel. And then the replacement consists of a call to a CELU and mol quant kernel, which performs both operations at the same time. And the really nice thing about the pattern matcher is that we can register both the pattern and the replacement as regular Python functions, and they get traced in kind of basically the same way as the regular model and function gets traced in Torch compile with fake tensors, and then they produce FX graphs, and those produce FX patterns, which then can easily do pattern match and replacement on the FX graph. So the performance improvements can be pretty decent here. So we're looking at Llama 405B, quantized to FP8 on 8 MI300s. And on the left, we see throughput versus the number of prompts that we're running through vLLM. On the right, we just see kind of the speed up between the fused and unfused code. So there's three columns here, right, for each number of prompts. The default, the blue one, that's using Torch compile without using custom kernels. The red one is Torch compile with using custom kernels, but without this custom fusion. And then the yellow one is with custom kernels and with fusion, right? And so we can see that with fusion and with custom kernels, we slightly outperform the default, but custom without fusion can actually be slower. So yeah, this default torch-based implementation actually by Torch 2.7 has gotten really good. So Torch compile has actually gotten good enough where sometimes it outperforms our custom kernels, including this case. But the fusion is still better here because we're using a custom quant kernel. And the obviously on the graph on the left, it's harder to see the improvement. So yeah, on the right, we kind of see just the improvement between the fusion and the default. So you can see it goes up to like 8%, on average, like 3-4%. And that's pretty good because quantization is a total of 8% of model runtime. So if we removed all quantization operations, we would still only get an 8% improvement. So this is a pretty good improvement that we're getting here. Uh, and yeah, so the numbers we saw earlier are from the CLUML and QuantFusion, which I described the example of, and also RMS norm and QuantFusion, both of them turned on. We also have this sequence parallelism pass that we're very proud of because it was actually a community contribution, and it really just goes to show that we've built a good system to add these custom passes and made it easy to do so. We also have two passes that do one does no-op elimination, one does some functionalization adjustments, which are kind of complementary graph optimizations to aid Inductor in doing some custom graph modifications that helped us. And coming soon is an attention and quant fusion. So while RMS norm and CLUML might be replaced by torch-based implementation, so these fusions won't be as useful anymore. Attention is likely to stay a custom operation because it is so important for performance. So we're really excited about this attention and quant fusion pass. Finally, I want to quickly mention just how custom passes can be added. Obviously, the first way is to add them to the Postgrad Pass Manager, which is just a Python class that runs these custom passes and manages them by modifying the vLLM source code. But we also have ways to add them without touching vLLM source code. So either on the command line, use the -o or -- compilation config flag, kind of like Richard showed with the key inductor passes, or doing the same in offline mode by specifying the compilation config object with the same structure as above. And this is really great because if anybody has a use case where they want to make custom transformations on the Torch FX pass, whether to insert custom kernels or just like change around the structure or do anything else, they can do that without modifying vLLM source code. So yeah. I guess let's jump into the discussion. I'll give it back to you, Sasha.
Yeah. Thanks a lot for the presentation, guys. I think that was really cool. I think there's already a good bit of number of questions already popped up in the chat. So I guess one question from Ford Shaper is how large are the artifact files as related to overall model size? I don't actually know this one. So Richard, maybe like talk a bit about like the
Yeah.
what is a serialized torch compile graph like order of magnitude, kilobytes, megabytes?
It's say megabytes. So what is serialized? We do not serialize your model weights. Those just come from your model. What we do serialize are just the intermediate graphs. The intermediate graphs like are just like O of like your model source code, like however big your model is. So we serialize intermediate graphs. We also store the threading kernels and their compiled artifacts, like the cubins. That is the part that can actually be big. And so that's where I would say like megabytes, depending on how many like threading kernels were actually compiled.
Yep, that makes
Well,
sense.
I was just asking, thanks for the answer, Richard. I was just asking because you were talking about moving the artifact files and the cache like from uh, system to system so that you can get a warm startup. And I was curious if you had done any testing with like loading those compilation files from shared storage or something like that that you have mounted to different nodes as you load them independently, I guess.
We have done testing with this. It works. It depends on how much storage you have, I guess. They are not as big as your model weights.
Right. Cool. Thanks.
Yeah, great. There's a question from Sangeeta on how auto-tuning actually works. Is it done every time for a kernel launch? I think that's not true.
Yeah, there's two types of auto tuning. Like the there are some heuristics for whether we do it at compile time or at runtime. If we do it at compile time, then it's like when you're compiling a model, like we
If we
will.
do it at compile time, then it's like
Oh,
I heard an
Stephen.
echo.
Yeah, maybe you can mute Stephen.
Okay, so if we do it at compile time, then we basically just generate some dummy inputs based on the shapes of your inputs, and then we just run those, and like we pick the best kernel, and then we won't auto tune again unless there's a recompile. If we do it at runtime, then it's the first time the kernel is run, we will do set auto tuning with some real inputs. So we try not to like redo this a lot. There's also a separate auto tuning cache that will just cache like the best kernel.
So I have a follow-up question. So in vLLM, by default, is it done at compile time or at runtime?
Sure. VLM, sorry, it's a mix of both. Oh, sorry, let me walk that back. When VLM does the model like warm ups, the model bring up and warm up on a cold start, it actually does some running of sample inputs with your model, and that's when the auto tuning will happen. During model serving, there is no compilation, there is no auto tuning.
So how that it will work if inputs are changing, right? So with different requests, number of prompts is changing, and the size of the sequence length is changing, then how
Sure.
that will scale?
Yeah, torch.compile auto tunes with like the first size you give it, which is not always the best size to like run on.
Mhm.
So there are performance opportunities to specify like static like shapes. Like you would specify exactly what batch size you're using, and then
Mm.
torch compile like, can give you a really fast auto-tune kernel for said batch size. That's at the trade-off of more compilation time.
Okay, sounds good. Thanks.
Yeah, there's a question from Pratik on, are there heuristics that we can follow that allow us to determine if a given tensor operation is compute bound or memory bound? Um, this is a great general question. I think this would be nice to have, but it does kind of bring up an idea I've had maybe slightly separately for like different methods like speculative decoding, where or like optimizations where you want to know, oh, if I run a model forward pass with like n number of tokens, how compute bound or how memory bound are we going to be? Um, and torch compile might actually be like a good place to kind of like get like a flop count for a graph, um, or like a relative arithmetic intensity. Um, so is that something that is there anything in torch compile for that kind of infrastructure, if that makes sense?
Yeah, if you turn off torch compile, like we have this thing called a flop counter. Like it's somewhere in torch.utils. It's like torch.utils.flop counter, and it's a context manager. You put it there, it'll tell you how many flops your operations took. I don't know if that answers the question though.
Yeah,
Like
yeah. I
I
mean, like, so yeah, we you could probably build something to Pratik, that you know you take like how many gigabytes your model is and probably KV cache and get the number of flops from Torch and you know make an arithmetic intensity, you know,
If I
flop.
can just add something, I just want to take a step back because I know we have a lot of people on this call, and not everybody might be like as in the weeds in terms of this. When Michael says arithmetic intensity, that's basically the ratio of computation to memory operations. And the higher the arithmetic intensity, that means you're doing more for every memory load, and that's generally better because you want like you're limited in terms of like the computation you want to do. Like if you're serving an LLM, like there's a certain amount of computation that you want to do. So you want to reduce kind of the memory that you're doing during that. And then taking even another step back, like usually on new hardware there's a lot more flops, so like compute operation capability, right, per second, than there is bandwidth, so memory capability. So I think for me, kind of like a very simple, kind of common sense approach is just if something is element wise, so if you're just like processing a tensor, like one element at a time, usually that's going to be memory bound because you're doing like roughly the same amount of memory and computation, and there's a lot less memory capability than computation. And then something like attention or a gem, right? It has a lot more compute than memory, so it'll be more often compute bound. But for that, you need kind of like similar shapes. Like if you have a matrix multiplication, but one of the matrices is really thin, or maybe even just a vector, then again, you go back to kind of like similar amount of memory and compute. That's like a very high level explanation of that. Hope that helps But I think also like what Michael's talking about, directly measuring this would definitely be helpful because a lot of times we kind of make these like guesses and until you measure, it's hard to know.
Yeah, thanks. That's exactly what I was looking for.
Yeah, I think we could definitely actually use some of these heuristics to have better defaults in vLLM, like with respect to like default chunk prefill size and things like this. Yeah, so interesting thought. Yeah, are there any other questions from folks that want to come off mute or in the chat?
Yeah, I wanted to know exactly how Inductor, has a library of kernel templates and sort of um, how it goes about sort of building the candidate kernels and code genning it. Can you comment on that? Like, does it have, is it only as good as these pre-templates that have been uh, provided to it?
Yeah, most of the performance from Inductor is not from the templates. Like we do have templates for things like attention. We have templates for things where like we will try to pattern match like a sequence of ops that looks like attention into being attention. That's not where most of the performance comes from. Inductor will just like given like point-wise operation, most of the performance comes from Fusion. Given like point-wise operations, Inductor takes the graph. It has this separate like scheduling and cogen phase, but where it will take the point-wise operations and it will just straight up generate a Trident kernel for you. Like if you're just doing point-wise operations, you can just imagine Inductor reading through them one by one and just generating like the corresponding Trident, like the corresponding TL operation for it into a Trident kernel. Something similar happens with reductions, but I'm not as clear on what happens there.
Yeah, I mean, some of our experimentation found that, I mean, maybe we weren't doing it very optimally, but the torch.compile based fusion actually um, did better than custom Triton fully fused kernels. So would
Yeah.
be nice to have some tools to sort of investigate that in more detail.
Yeah, so if you do torch logs equals output code, that's an environment variable. It will just dump out the Trident kernel that Inductor produced, and then you
Yeah,
can just stare at that.
we did look at it, and I think one of the things there we noticed is that it leverages sort of overlapping computation and communication,
I see.
which is, I think, a cool optimization.
It's not completely aware. I was not aware that Inductor did that, but that is cool. I agree.
I mean, I've seen things related to streams and things, so still learning. Sorry.
I guess, yeah, I'm actually curious on this, Richard, for the like fusing element-wise onto matmals. Is that something that happens, or is it more common that it'll just dispatch the matmal to like kublas or whatever, and then do the element-wise all fused in one kernel after that?
Yeah. By default, like if you do not pass torch compile any settings, like and also by default in vLLM, like it will just do the mapmul like in kublas and then element wise separately because it's not always profitable to fuse them. With max autotune in torch compile, or if you pass compile sizes to torch to vLLM where it will trigger the max compile, we will autotune like the mapmul, like a kublas mapmul plus element-wise operation, like an epilogue, versus a Trident kernel mapmul with the point-wise operations just like in the Trident kernel, fused into the Trident kernel, and then like we'll pick which one of the two are the best.
Yeah, interesting.
Are there good docs that sort of describe what you just sort of say? I mean, I got the last part about
Yep.
just patching in point-wise operations into the Triton MacMul. But yeah, I feel like this area deserves more documentation slash insight.
I agree. Yeah, the team has it. PyTorch Revive team, like we have it on our roadmap to just document like what Inductor does better so that people know like roughly what they're going to see when they use torch compile.
There's a new question from Chris. Um, Can you speak to why some model authors might not want torch compile to be enabled? Um, torch compile sounds like it may be a startup time performance hit, maybe only an initial one-time startup hit. So why might model authors disallow it? I'm not sure. Was there talk of
I
specific?
think, yeah, I think I know this. I think that it's not about disallowing. I think it's more about like, we had a bunch of model definitions before we had Torch Compile, and so then we started adding Torch Compile support to models by doing the at supports Torch Compile on the model class. But I think a lot of models just like haven't done that, and we just haven't gotten to it. So I don't know of anybody who didn't want it explicitly, because also like just enabling it doesn't mean that it'll necessarily get used. It can be disabled with enforce eager, right? So if somebody really doesn't want that like startup time hit that you describe, which I agree, right? There is some hit with compilation. It can still be disabled. So it's not like enabling it for a model that means that like you have to compile. Um, but I think it's mostly just people haven't added support because different models, like our add supports Torch Compile decorator will try to detect like the batching dimension and make it dynamic and all that. And that detection code doesn't necessarily support our models. I actually don't remember, Michael, you might know this about what the multimodal support is for Torch Compile, but I think that might not be supported. So I think it's just like support hasn't been added rather than like disabled, if that makes sense.
Yeah, I think it's like level of effort if like something about model definitions need to change or or and also whether it's worth it. Yeah, I mean I think for instance like we for vision language models like we don't run torch compile or even CUDA graphs I believe on like the vision encoder. But we do on the shared language model backbone because that's the majority of where the compute is. That's the majority of where the memory bandwidth requirement is. Um, and yeah, so um, not to say it would like hurt to put it there, but it's kind of like not as important as having it on the language model backbone. And similarly, putting it on every single model, even if all models aren't used super highly, it's a level of effort thing. Could be a good first issue to try and add some model to support torch compile that doesn't currently.
Another thing is, I think there's some initial Cutlass code generation also now supported. So, do you expect to use more Cutlass code gen in future? Is there a roadmap for that?
Within torch compile or
Yeah, as a backend for Torch compile, meaning to
Uh,
code gen Cutlass or fuse Cutlass.
Answer is yes. Like we are looking into that. We actually have an option to do Cutlass plus Mevels, Cutlass, Mevels, and fusions into those. Like right now, I don't remember what it's called, but you can probably find it in the Torch inductor config. But yes, we're looking into using Cutlass more.
yeah, I think I saw some of this for like the MX FP formats and stuff that you're messing with in Torch.io. Um, so yeah, hopefully the Python Qt DSL is useful for that. Okay, well, we're basically at time, so we'll just close things off here. Thanks for all the questions, and feel free to catch us in the Slack, vLLM Slack afterwards. As always, if you want to get involved with vLLM more, we encourage you to contribute, to make comments on PRs or issues that interest you. Your feedback directly helps us know what are the most important issues to work on. Um, and of course, as always, give us feedback, let us know both within the vLLM project or in office hours, how things are working for you, how can we accommodate you better. Join the Slack, it's very active, tons of people there. And of course, if you want to work on vLLM or other open source projects, we're hiring at Red Hat and other places to have more people working on this. So thanks a lot, and we'll see you at the next one on in June. Yeah.
And yeah, feel free to reach out to both me or Richard or Michael or anybody in the vLLM stack. We also have a hashtag sig-torch.compile Slack channel. So definitely feel free to ask questions there as well.
Yeah. Okay. Great. Thanks, everybody. Have a good week.